There is a sensation so common, so quietly persistent, so embedded in the fabric of every single moment of your waking life that you almost never stop to question it. Right now, wherever you are sitting or standing, something is pressing against you. Something is holding you in place. Something is orienting your entire biological existence toward a single direction, toward the ground beneath your feet. And for the vast majority of human history, the explanation seemed almost embarrassingly simple. Heavy things pull lighter things toward them. Mass reaches out across empty space and grabs. Isaac Newton gave this intuition its mathematical clothing, and for over 2 centuries, that clothing fit well enough that nobody thought to look underneath it. But underneath it, the universe is doing something far stranger, far more beautiful, and far more geometrically precise than any simple pulling force could ever describe. The real answer to why mass creates gravity has nothing to do with reaching, nothing to do with invisible threads stretched across the void, and nothing to do with a force in the traditional mechanical sense. The real answer is that mass does not pull anything at all. Mass sculpts the geometry of the environment through which everything else must travel. And once you absorb that statement in its full mathematical weight, the universe you thought you understood becomes an entirely different place. To begin dismantling the old picture, we need to confront what Newton himself admitted. His law of universal gravitation described gravity with breathtaking precision. It told you how strong the effect would be, how it weakened with distance, how it scaled with mass. But Newton never once told you what gravity actually is. He described the recipe without ever identifying the ingredient. In his own correspondence, he referred to the idea of one body reaching out and acting on another across empty space with no mediating mechanism as so great an absurdity that no man of philosophical thinking could ever subscribe to it. Newton was troubled by his own theory. Einstein resolved it. The resolution begins not with objects in space, but with the nature of space and time themselves. Before Einstein, space was the passive stage on which physics performed. Time was the universal metronome ticking at the same rate for everyone everywhere. They were background features of the universe, absolute and inert. Einstein demolished that picture so completely that it is almost difficult to convey how radical the shift truly was. He showed that space and time are not separate passive containers. They are woven together into a single 4-dimensional structure, and that structure is not rigid, it is physical. It responds to the presence of energy and mass. It bends, it stretches, it curves. And it is precisely that curvature, that geometric deformation of the unified fabric of spacetime that we experience as gravity. Now, there is an analogy that opens the door to this idea remarkably well. Imagine stretching a thin rubber sheet across a large frame, like a trampoline pulled taut. In the absence of anything sitting on it, the surface is flat. A marble rolled across this surface travels in a perfectly straight line. There is no deviation, no curvature, no tendency to drift. Now place a heavy bowling ball at the center of that sheet. The weight of the ball creates a depression, a smooth valley that deforms the entire surrounding surface. The geometry of the sheet has changed. Now roll that same marble across the sheet near the bowling ball. It does not travel in a straight line, it curves. If you give it the right speed and the right initial trajectory, it will circle the bowling ball in a stable orbit. And here is the critical observation that separates this picture from every previous conception of gravity. The bowling ball is not pulling the marble. There are no invisible strings connecting them. The marble is simply following the natural geometry of the surface it inhabits. The environment itself has been reshaped, and the marble is doing nothing more than following the straightest possible path through a curved geometry. The universe operates in this precise manner, except in 4 dimensions rather than 2, and the fabric being deformed is not rubber but space-time itself. When a planet like the Earth concentrates enormous amounts of mass and energy in a relatively small region of space, it curves the 4-dimensional geometry of the space-time surrounding it. The Moon does not stay in orbit because the Earth is pulling it with some invisible gravitational rope. The Moon is following what physicists call a geodesic, which is the 4-dimensional equivalent of a straight line through curved spacetime. From the Moon's perspective, in the absence of any other force, it is simply moving as freely and as naturally as any object can move. It is the shape of the spacetime geometry that dictates the path. But to truly understand the depth of what Einstein discovered, we need to sharpen this picture significantly. Because the trampoline analogy, powerful as it is, omits the most profound and frankly the most philosophically shattering aspect of the entire framework. The trampoline curves in space only. What Einstein showed is that the warping produced by mass is not merely a warping of space, it is a warping of time. This requires us to understand something about how physics treats time in the relativistic framework. Time is not simply a clock on the wall. Time is a dimension, and it enters the equations of space-time geometry on the same mathematical footing as the three spatial dimensions. The metric tensor, which is the central mathematical object in Einstein's general relativity, encodes the geometric relationships between every pair of events in spacetime. It tells you the distance between points not just in space but across the full four-dimensional continuum. When mass is present, the components of this metric tensor change, the geometry shifts, and crucially, those shifts apply not only to the spatial components but to the temporal component as well. Mass does not just bend space, it bends the rate at which time flows. This temporal warping is not a theoretical abstraction. It is physically measurable. It is confirmed by atomic clocks placed at different altitudes. A clock sitting on the surface of the Earth, deep in the gravitational field, runs measurably slower than an identical clock orbiting far above it. The global positioning system that guides navigation around the planet must account for this effect continuously. If the engineers ignored the relativistic time dilation between the satellite clocks and the ground-based receivers, the accumulated errors would render the entire system useless within a matter of minutes. Gravity slowing time is not philosophy, it is engineering reality. Now here is where the physics becomes something close to magnificent. If time flows at different rates at different locations near a massive object, then there is a gradient. Time flows faster at greater distances from the mass and slower as you approach it. In the language of general relativity, the future itself is oriented toward regions of slower time flow. Objects moving freely through space-time, following their natural geodesic paths, naturally drift in the direction of decreasing time flow rate. They move toward the region where time runs the slowest. Near the Earth, that region is the surface. And what we call the gravitational pull toward the ground is precisely and mathematically identical to every freely moving object following the gradient of time through the curved space-time geometry that the Earth creates. Let us now bring this home with an example so intimate it is almost uncomfortable. Consider your own body as you sit reading or listening to these words. Your head is slightly farther from the center of the Earth than your feet are. That distance is small, only a meter or two, but it is physically meaningful in the relativistic framework. Time at your feet is passing ever so slightly slower than time at your head. The difference is minuscule, a fraction of a second across an entire lifetime. But the gradient exists, and because of that temporal gradient in the geometry of space-time, your body is experiencing what we perceive as the sensation of weight. The pressure you feel pressing you into your chair is your body resisting the geometric instruction of space-time. If the chair were removed, you would not be pulled downward. You would be released. You would follow your natural geodesic path through curved space-time and accelerate toward the ground, not because something grabbed you, but because the geometry of your local space-time environment dictates that this is the straightest path your four-dimensional trajectory can take. This leads directly into one of the most powerful and elegant conceptual foundations of general relativity, which Einstein called the equivalence principle. Einstein arrived at this insight and later described it as the happiest thought of his life. The principle states that a person standing in a gravitational field and a person accelerating in empty space with no gravitational field present would have no way of distinguishing their situations through any local physical experiment. A person in a sealed elevator sitting on the surface of the Earth would feel pressed to the floor. A person in a sealed elevator being accelerated through empty space at the same rate would feel pressed to the floor in an indistinguishable way. Gravity and acceleration are locally equivalent. You cannot tell them apart from inside a closed room. But the reverse statement is equally important and even more illuminating. If you were to cut the cable of that elevator and allow it to fall freely toward the Earth, the person inside would feel weightless. They would float. Every object released in that freely falling elevator would remain suspended relative to them. From their local perspective, in their immediate environment, there is no gravitational field. The gravitational effect has been locally erased by the free fall. And this, in the relativistic framework, is the deepest statement one can make. The person in free fall is actually in an inertial frame. They are the ones moving naturally, following a geodesic, undisturbed by any genuine force. The person standing on the surface of the earth is the one experiencing a real force, the normal force of the ground pushing up against them, preventing them from following their natural free fall trajectory. The ground is what is doing the pushing. Gravity, in the Einsteinian sense, is not a force at all. Weight, the sensation you feel in your body right now, is not gravity. It is the electromagnetic force of solid matter stopping you from falling. To put the mathematics behind this in its proper context, we need to visit the Einstein field equations. Published in November of 1915, after years of intense intellectual struggle, these 10 coupled nonlinear partial differential equations represent perhaps the most compressed and profound description of physical reality ever written. On one side of the equations, you have the Einstein tensor, which describes the geometric curvature of space-time. On the other side, you have the stress-energy tensor, which describes the distribution of energy, momentum, pressure, and matter in spacetime. The equations state, in their mathematical entirety, that the geometry of spacetime is determined by the distribution of energy and matter within it. The curvature on the left is set by the energy content on the right. John Archibald Wheeler, one of the great relativists of the 20th century, summarized the content of these equations with a phrase that has become legendary in physics. Mass tells spacetime how to curve. Spacetime tells mass how to move. This is not merely a poetic simplification. It is a precise description of the feedback structure encoded in the field equations. The presence of mass and energy curves spacetime. That curved spacetime then determines the geodesic paths along which all matter and energy must travel. The result of following those geodesic paths looks, from the outside, precisely like gravitational attraction. But no force has been exchanged, no signal has been sent, no invisible thread has been stretched. The geometry itself is the physics. One of the most striking consequences of this geometric picture involves the behavior of light. Photons, the quanta of electromagnetic radiation, have no mass, and yet they follow geodesic paths through curved spacetime. Near a massive object, the geometry of spacetime is curved, and so the geodesic that a photon follows is not a straight line in the Euclidean sense. It is a curved path through the warped four-dimensional geometry. This gravitational lensing of light was confirmed observationally during the solar eclipse of 1919, when measurements of starlight passing near the edge of the sun showed the predicted deflection angle from general relativity. The confirmation made Einstein famous across the world overnight. But the deeper significance was not simply that light bends near massive objects. It was the demonstration that even massless entities are subject to the geometry of spacetime. Gravity was not about mass attracting mass. It was about the geometric structure of spacetime governing the motion of everything. And yet the question that deserves to be pressed even further is the one we started with. Why does mass create this curvature in the first place? This is a question that general relativity itself does not fully answer. The Einstein field equations tell you precisely how a given distribution of energy and matter curves spacetime, but they do not tell you why energy and matter have this property. This is one of the deepest open frontiers in theoretical physics. The attempt to understand gravity at the quantum level, to build a theory of quantum gravity that reconciles general relativity with quantum mechanics, is one of the central unsolved problems in all of science. String theory, loop quantum gravity, and causal dynamical triangulations each represent different attempts to answer this deeper why, to find the microscopic origin of spacetime curvature itself. None has yet achieved the complete and experimentally confirmed resolution that physics demands. But what we do have is already breathtaking. We have a theory that replaces the mystery of action at a distance with the clean mathematical language of differential geometry. We have a framework in which the universe is not a collection of objects pushing and pulling each other through an empty void, but a single dynamic geometric structure in which the distribution of energy sculpts the curvature of the arena, and that curvature in turn dictates every trajectory through every moment of time. We have a picture in which your weight in your chair right now is not the passive consequence of an invisible attractive force, but the physical manifestation of a geometric gradient in the flow of time across the meters of your own body. The universe is not held together by mysterious, invisible forces of attraction. It is shaped by geometry. And the geometry is not the static backdrop of reality. It is reality itself, dynamic, responsive, curved by every gram of matter and every joule of energy distributed across its four-dimensional expanse. When you look at the sky and watch a satellite pass silently overhead in its orbit, you are not watching an object being held by an invisible rope. You are watching an object follow the most natural path available to it through the sculpted geometry of the space-time that the Earth has carved into the fabric of the universe. And somewhere in that